Okay, welcome back to this series of tutorials for OCR GCSE Computer Science. We're going to look at paper 2 today, and I believe it's going to be the first of 2 tutorials because there's quite a lot of content that I want to go through, because paper 2 is a lot more about certain skills that you're going to need to demonstrate. A brief recap: hopefully you're getting somewhere between 7 and 8.5 hours of sleep a night. And hopefully you're seeing the benefits of that. A few other quick study tips then, apart from sleeping well, eating well and exercise, would be to actually change your revision location. So each time you revise, try and mix it up a little bit and study in different locations. The reason why is because your brain works through the series, it benefits from cued recall, which suggests that not only do you remember things not only do you recall things from your neocortex, but you also recall where you first learnt them as well. So by varying your study location, you're just giving your brain another anchor point and another neural pathway to access that same information. So actually, while some people think you should study in the same place all the time, actually varying it, provided that the place that you're studying is quiet, has a desk, is well organized, somewhere where you can write undisturbed, then that would be beneficial for you. I'm going to put a few more links below in the comments or extra notes section, which will give you some other quick advice on revision techniques. But what we're really here to do is look at paper 2. Let's start off firstly with sampling sound. So sound is generally measured as an analog wave, this smooth wave here. When we sample it, the process of sampling is essentially converting this analog wave into a digital one. All of these points here essentially show the sampling frequency. So let's say if the width of this box is a second, we could say that in this sample, the sample frequency is 10 hertz. So you're sampling you're taking 10 samples every second. And you'll see that the curve is a lot closer to the original analog wave when you have a higher sample frequency or a higher sample rate, as for when you have a lower sample frequency. Here you only have 2 sample points, therefore it's approximately the same shape as the original analog wave, but it's not exactly the same, and the sound played back is not going to be the same at all. Another thing that we need to consider when we are looking at sound is the bit depth. So that's the number of bits each sample will be given. It's sometimes therefore called the sample size. So let's say if every sample you take only has, say, 1, 2, 3, 4 bits of accuracy, you can see that it's going to contain a lot less detail, and it's going to be, the sound is going to have a smaller dynamic range. It's not going to be as accurate and true to the original analog wave as if we have a high bit depth. So I think here there are probably, say, 20 lines. So generally the bit depth is measured in binary numbers like 8-bit, 16-bit or 32-bit. If you've got a 32-bit bit depth, what that means is every single sample that's taken is 32 bits. And if you're taking 10 samples in a second, then I suppose you've got 320 bits per second. The other thing you need to consider, though, is the number of channels. So in most audio files that are stereo, you're going to see 2 channels, the left channel and the right channel. So something coming through the left speaker, something coming through the right speaker. And on this occasion, you'll see the sound in both the left and the right channel is the same. In, say, surround sound, you might actually have 5 channels, therefore you're having more data. And in a mono track, say for example on the radio, you only have 1 channel. so you've got less data. So how do we calculate the file size for an audio file? Well, first of all, the first useful formula is based on the sample frequency, which is measured in hertz. We multiply by the bit depth, which is in bits, and we multiply by the number of channels. That gives us the bit rate. As you can see here, that's measured in kilobits per second. So what that tells you is for every second of audio, it's going to be a certain number of kilobits. So in order to work out the file size, guess what we have to do? If that's per second, all we need to do is multiply by the duration, which is in seconds. So the file size of an audio file is the sample frequency in hertz, multiplied by the bit depth in bits, multiplied by the number of channels, which is usually 1, 2, or say 5 channels if it's surround sound, multiplied by the duration. In some exam questions, it might give you a mathematical formula and say, for example, you've got a sample frequency, let's just make it easy here, of 10,000 hertz or 10 kilohertz, a bit depth of say 8, and then you've got 2 channels and a duration of say 100 seconds. You might multiply those all together and find that it doesn't quite match the file size. And the reason why that is because you will have some metadata as well. So metadata might include things like the file format, the duration. Actually, the metadata would be all of these things. So the file size would be all of these multiplied together plus the metadata. But if the metadata is not given, this is a decent enough approximation. On to images now. If we're going to calculate an image file size, it's a very similar concept really, but this time we're dealing in pixels. So let's say, for example, we've got a width of 800 and a height of 600. We times those two together and you're going to end up with 48 with 4 zeros, so 480,000. And then you're going to times by the bit depth. Now the bit depth is always determines the number of colors that you can see. In this logo, there are only 2 colors, black and white. Therefore, you can store that in 1 bit. Because if you were saying black, that could be 0, and if you had white, that could be a 1. So the simple formula here is 800 by 600 by 1. The calculation there is clearly incorrect. Should be, because 8 6 are 48. So 480,000. And then you would take that 480,000 and divide it by 8. Should have really proofread these slides, but it's good to be able to spot our errors. And in your exam, this is exactly what you need to do. You need to go back over and check your answers, because frequently we find students who know the formula, but they've made a silly mistake like myself there and have done 8 times 6 and they've put 24 instead of 48. So it's 480,000 bits. But in order to get into bytes, you might say, for example, divided by 8. If we're dividing that by 8, then you would get 6,000 bytes. If you were asked to give that in kilobytes, it would be roughly 6 kilobytes. You could approximate and use 1,000. You won't be expected to divide by 1024 without a calculator in your exam. Okay, well, what happens if you've got more colors? How do you work out the bit depth then? So here, for example, you've got, let's say, for example, we've got 16 colors here, or a possibility of 16 colors. You're only actually seeing black, red, yellow, and maybe a white background. So if you're only showing those 4 colors, you could store it in 2 bits. But let's assume that we're storing a bit depth of 16 colors. Effectively, what we're doing is we're trying to find the exponent. So 2 to the power of 4 gives us 16. So we know that the bit depth is therefore 4 bits. So multiplying this then, we should have 800 by 600 by 4. And let's just double check that on paper. So I've got 48 times 4. This is obviously wrong. So 32, 4 times 4, 16, 190. Actually, this is correct. So it's 1,920,000 bits. In order to work that out in bytes, remember what we're going to do. We're going to divide by 8. Hopefully that's what you got as well. And therefore, you've got 240,000 bytes, which is roughly, if you just divide by 1,000, 240 kilobytes, or 0.2 megabytes. Okay? So those are a few of the calculations which I think are going to be really useful for paper 2. We've got 10 minutes remaining, so let me have a look at some other skills which will also be useful. We might as well stick with our calculations and move over to check digits. So let's have a look at this here then. So I've got the formula up there at the top here. And if we're given, say, this 8-digit code, they'll usually give you an algorithm as to how you would calculate the check digit. Let me get this larger so you can see that on the recording. And we'll go full screen. That's not full screen. Maybe it's because I'm recording, so it won't give me full screen. But that's pretty good, right? Let's just go through this then. They'll generally give you the rough algorithm, but in this case, we're essentially using like a ISBN type of algorithm where each digit has a weighting. And we put those in here. I'm using pencil for all my calculations, so that if I make an error, I can go back and correct my mistakes easily. Whereas in pen, it's just going to get really messy in the exam. Of course, we need to go back over our answers in black pen afterwards so that the exam can be marked accurately. How do we know what the weighting is? Well, the check digit in ISBN always has a weighting of 1, and then it increases. So in ISBN, you might have 11 digits, but in this case, we've only got 8 digits in the code. We're trying to work out what the check digit is. So in here, following the rules for ISBN, we're multiplying the two together. So we've got 16, 21, 5 times 6 is 30, 5 times 4 is 20, 8 4s are 32, 18 and 10. We're going to add those all together. So 16, 21, 30, 20. You won't have a calculator, so this is how I'd recommend you do it in the exam. 10, 11, 17, carry 1, 3, 6, 8, 11, 13, 14. So you're going to get 147, yeah? We need to do 147 divided by 11 and figure out what the remainder is. So in your exam, once again, you won't have a calculator, so what I would advise you to do is just write out the 11 times table on the side so that you can quickly reference that. Whoa. 121, 132, 143, 154, 165, 176. I mean, we only need to go to 147 anyway. So this is times 10, 11, 12, 13, 14. Essentially, we've gone to 143, and we've got a remainder of 4. So if our remainder is 4, because we're doing 147 mod 11, and we're getting a remainder of 4, then what we should do 11 minus 4, and what we should get is our check digit, which is 7 here. And what you could do is you could also add this in just to check the weighting's correct. So if we do 7 times 1 is 7, the original figure was 147. Let's say, for example, we add that 154, we can see the check digit is correct, because if you did 154 mod 11, you'd essentially get this number here, and you get 0 as your remainder. Therefore, this check digit is accurate. In terms of possible check digits, if it ever goes up to 10, then the check digit is X. But there's a few for you to practice. You can just give yourself a load of numbers to practice there. And if you have the purple revision guide, the Pearson one, if you go to page 78, you'll see some exercises there. If you've got the revision workbook, it's page 78 again, and you'll see some of those challenges there that you can do. Okay, 7 minutes remaining. Let's go through now, please. Arrays. I'm going to move this paper out of the way because that's going to get slightly confusing. So let's put it on the floor. And let's just look at this here. So we're going to go through arrays first, and then we're probably going to go on to 2D arrays in the next video. But let's examine the code first. It says here we have, I'm going to zoom in slightly so that we can see that nice and clearly. Okay, good. So the following pseudocode adds up the total of every element in an array called X. And you'll see this is typical OCR kind of pseudocode, yeah? The output is 12. Explain the error. So if we look through here, what it's meant to do is it's meant to add up all of these. So it's meant to do 9 plus 4 plus 5 plus 6 plus 7 plus 12, which would give us 18, 24, 31. So it should give us 43, and it actually gives us 12. Have a look at this. There's a for loop here which goes to the length of X. So for count equals the length of X, which is 1, 2, 3, 4, 5, 6. The total equals X count. So what's happening here then is when it says print total, what it's actually doing is it's just saying total equals X count. And I imagine the last output is 12. What's happened is it's actually just outputted this element here, yeah? So it's gone 0, 1, 2, 3, 4, 5, and stopped there, and then it's output 12. So the error is that, well, first of all, we should explain the error. This is a logic error because the code runs, it just doesn't produce the correct result. So we should say the program should produce an output of 43 by continuously adding to total. Notice how I use more space than is necessary. I always give more detail than is necessary, to be honest, just in case. By continuously adding to total, there, however, here it simply outputs array X, and it's gone to 0, 1, 2, 3, 4, 5. It's just gone to 0, 5, which is equal to 12. Rewrite line 6 so the total of the array is displayed correctly. So if I want the total to be displayed correctly, then this line here, rather than total equals X count, we need to do a running total. So we need to do total equals total plus X count. And what that will do is the first time it'll add 9. 9 will become the total. Then we add 4 to it, so it'll become 13, then 18, then 24, and 31, then 43. Rewrite lines 5 to 8 so the mean average is output. So when we're calculating the mean average, what we need to do there then is we need a running total. We can keep total if we want, I suppose, and then just divide. So what is happening here then is if we want the average, we're still using the same count, so we can do, I would prefer for count equals and then we'll do, yes, actually x dot length is fine. Or you can do 0 to 0, 1, 2, 3, 4, 5, 0 to 5, and then it'll become inclusive. So for count equals 0 to 5, those of you who are writing Python, you might write for count in range 0, 6, because that's inclusive. But OCR pseudocode, if you can, for count equals 0 to 5. We're going to do our running total, so we'll say total equals total plus x count. And then rather than outputting our total at the end, we're going to do average equals total divided by 5. You could have done x dot length here as well, but it's total divided by 5. Whoa, that's not correct. There's 6 elements. So yeah, it should be total divided by 6. So this is like the beauty of using a pencil. Rather than like crossing it out, we could rub that out, and then we'll go back over it in pen later. So average equals total divided by 6, and then we can print our average. That's the bell, so I'm going to stop there as I have great duty to go to. But when we return, we'll go into further arrays, 2D arrays, binary, and hex. I hope that's been useful.